Mathematical cryptography, the eigenvalue enigma. Hidden within every matrix lies a polynomial waiting to be decoded. Today, we're cracking the code of the characteristic polynomials that reveal a matrix's deepest mathematical DNA. Join me as we transform abstract symbols into breathtaking mathematical narratives, unveiling how linear transformations truly work. So, in our problem today, A20, the first, second, and last coefficients in the characteristic equation A.73 are Cn equals -1 to the n, Cn minus 1 equals -1 to the n minus 1 times the trace of the original matrix T, and C0 is equal to the determinant of T. Now, this holds for this book's formalism. In a linear algebra text, we have lambda I minus a, which would make these leading coefficients different. Note that this is -1 because we have a minus lambda I, or t minus lambda I. So the negatives are inherited on the lambdas, but in other books, this is not true. So be aware of that. As far as this goes, the trace and determinants, they keep coming back over and over again, so be mindful of that. So for a 3 by 3 matrix with elements t sub ij, what is the coefficient sub 1? Let's find out. So for a given 3 by 3 matrix, we have the components where we have 3 by 3, so we have 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3, so 9 elements total. Thus, to find the characteristic polynomial, we have to find the determinant of this matrix. So as we see here, we have t minus lambda I, so we see how the negative sign gets onto the lambda in the determinant, but in other books, when we have lambda minus the element, that's not always true. But for this book's formalism, this works out just fine. Either way we go, we have a determinant that needs to be equal to 0, so let's find out how to evaluate this. So now in the evaluation process of the determinant, as we've seen multiple times previously, it's common to use the first row. And so the cofactor signs come from plus minus plus, minus plus minus, plus minus plus, plus minus plus. So we're going to use the first row once again. As a result, we can break this into parts. So the determinant of t minus lambda I, we take the first component of the first row, and this is the ti or t11 minus lambda. That corresponds to this placement here. And then we have a subdeterminant or a minor determinant. And then we can evaluate that later. Then for this term right here, we have minus t12 times its subdeterminant. For this last term, 1 3, we have plus t13 times its minor determinant. So either way it goes, we have this broken down and do 3 2x2s now, but this gets messy quick, so we'll break this into parts as we see enumerated with 1, 2, and 3. Clearly, 1 is going to be the most trouble to deal with because we have 1, 2, 3 lambdas here. 2 only has 1 lambda, 3 only has 1 lambda. So we'll focus primarily on 1, and then we'll speed run 2 and 3. So in evaluating bracket 1, we see that we have plus t11 minus lambda, and then we do the crisscross on it. So we have a times d minus b times c. And now we see we need to distribute this parentheses with this one. Upon doing so, we see we take this, distribute it to that, distribute to that. That's what our first two terms are. Take this with the negative sign, distribute that in. So we get a plus sign there. Either way we go, we get everything we need to on these, so we're perfectly fine. Now we need to do the same thing and dump this t11 into all of those bracket terms and the negative lambda in all the bracket terms. Upon doing so, we get this, what looks like a jumbled mess. But as you see, after some color code, we see we have a bunch of what we would consider linear terms in lambda, denoted with the green, a bunch of quadratic terms denoted with the blue, and a cubic term denoted with the purple. Everything else that doesn't have a lambda on it is a constant term. So tidying this up together, putting it in its highest degree and then working down, so descending polynomial degrees, we only have one factor of negative, or one factor that is negative of lambda cubed. Factoring out all factors for lambda squared, we have t11, 𝚃22, 𝚃33, all the factors on lambda, which are quite a bit of them. We have negative, 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 and only one positive, so we have to be aware of that. And then we have this kind of machinery here where we have 1, 1 multiplied by 2, 2, 3, 3, and then 1, 1 with the 2, 3, 3, 2 mix. That'll be interesting, and we'll see why so in just a moment. So in part 2 of the determinant, we break it down into its AD minus BC, distribute the 2, 1 into its parentheses as we see here. Now we can dump this negative T12, and when we do that, we see that once again, changing signs due to the negative here, this negative make a positive, this negative makes a positive, and then here we have one linear term in lambda, everything else is constant, so factor that out like such, and put these signs in any order you want. What's important to note here is that we knew from part 1 that we had 3 lambda terms, right? So it made sense that we ended up with a cubic. In part 2, we only had a 1 lambda term, so it makes sense that we ended up with the linear. Part 3 was also much like part 2, so we're going to end up with another linear. So taking this, we have AD minus BC. Now this component needs to be carefully distributed because of the minus sign there. Once we do that, then we could dump the T13 in, run it through the same gauntlet, factor it out to put all the pieces together. And then when we look at the overall determinant in component form, we see that the determinant of t minus lambda I is equal to the cubic, quadratic, linear. This was all from part 1. Now when we add in the results of part 2 and 3, we see we get this and this. So all that parts 2 and 3 did was add 2 linear terms and a whole bunch of constant terms. But let's take a note real quick on what's going on this quadratic term, where you have t11 plus t22 plus t33. Well, this is nothing more than the terms of the main diagonal, and since we're adding them together, that's exactly what is defined as the trace. So when we simplify this, we see quite clearly that the trace can be written as just trace t. Solves a whole lot of problems already. Now, what we also notice is that the cubic term led with the -1, or a negative sign, which can also be represented by -1 to the 3rd power, okay? If we factor out all the linear terms lambda here, we see we get a collection of weird cross terms, but are all pretty much related, like 2, 3, 3, 2, 1, 2, 2, 1, and 1, 3, 3, 1. Pretty cool to see that. Or 1, 1, 2, 2, 1, 1, 3, 3, 2, 2, 3, 3. Pretty cool. They're all there is a form there, so we can reconstruct that. What I'd like to pay attention to here is that this constant term looks kind of jumbled. But what we note is that from part 1, we had a T11, T11. Since that was our cofactor, we can keep that in, our cofactor. We could keep that and factor it out. Similarly, our second term had a T12, T12. That was our cofactor, so we could factor that out. And then T13, T13, we could factor those out. So cleaning this up, noticing that we just go ahead, copy these purple and blue down, we rearrange the lambda in kind of ascending indice order. So 1, 2, 1, 3, 2, 3, and then put all the minus signs on this back half. Now what we see here is that upon factoring out the T11 from both of these terms, we get a 2, 2, 3, 3 minus a 2, 3, 3, 2. There's a cross structure there. Then when we see we have a 1, 2 factored out, we have a 2, 1 through 3 and a 2, 3, 3, 1. There's a cross structure there. And then finally, for the 1, 3, we have a 2, 1, 3, 2 and a 2, 2, 3, 1. There's a cross structure there. So this indeed should look familiar. Consider that the determinant of t was the determinant of all these without any eigenvalues. We see that the cofactor plus t11 minus t12 and plus t13, these have all the same terms, 2, 2 through 3, 2, 2 through 3, 2, 3 through 2, 2, 3 through 2. Similarly, 2, 3, 2, 1 through 3, 2, 1 through 3, 2, 3 through 1, and the like for t13. So if we expand these out as we see here, we see we get a 1-to-1 exactly as we saw there. So that's pretty darn cool, and we can reconstruct that. And this shows us that the constant term is nothing but the determinant of the original matrix. So by putting these together, we see we have a cubic term with the -1 to 3, a quadratic term with the trace on it, a linear term with a whole bunch of crisscross structures and matching indices structures that have minus signs on them, and then finally a determinant for the constant term. Now this last term can also be proven by setting lambda equal to 0. So that's another way to get that same result in another proof. Now, since the characteristic polynomial has the form of Cn lambda n, so for whatever n degree, then -1, and all the way through to a constant term, all that has to equal 0. What we can say is that for a 3 by 3 matrix, we know that n equals 3, okay? So our polynomial has to be at most a cubic, right? So we have C3, lambda 3, C2, lambda 2, C1, lambda 1, C0, lambda 0, which just goes to 1. So again, by fundamental theorem of algebra, we know that we can have at most up to 3 eigenvalues, but we're not really too concerned with that. We're more concerned with how do we actually get these descriptors of what the characteristic polynomial has in it. And when we do this, what we can see is that for 3 by 3s, if we have like a diagonal or a triangular matrix, we just have to look at the main diagonal because these things go to 0. And if most of these things go to 0, then they're bye-bye. And if we just have if most of these terms here would go to 0, then we don't have to worry about this term. And that reduces our overall complexity. Determinant, that's going to go to 0 because we're triangular. Here, the trace, all we have to do is look at the main diagonal. And since this is just a matter of signage on the lambdas, we still get the same result, but we can see that triangular matrices only have to be looked at as the main diagonal thanks to this trace property. One of these matching sets is always going to be 0, so all of this goes away. And because you have a lot of zeros in that cofactor, this is going to go away, except for maybe one term, which is the main diagonal term. Therefore, we know that C3 equals -1 to 3, which is what we see here. That's the coefficient on the cubic term. So generalizing this, we get Cn equals -1 to the n, and the constant term C0 equals the determinant. Again, this -1 to the n thing only works because we have t minus lambda I. If we had lambda I minus a, like in linear algebra books, this would not necessarily hold. Further, the second term we saw C2 in blue, the coefficient on the quadratic term was the positive trace of t. But this +1 can be written as -1 squared times the trace. So we can generalize that to Cn minus 1 equals -1 to the n minus 1 times trace. Very cool. Finally, we see that our C1 term, which was originally the question, is equal to a whole bunch of cross terms here, so symmetric style matrix entities, and then composites of the main diagonal and the composites of the composite products of the main diagonal elements. Very cool. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There is so much more to uncover, and I'd love to have you along for the journey. I also just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. Believing in this journey. Oh, I can't even speak. And if anyone else is interested in supporting the channel and supporting our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.